This is lecture 8B on the hydrostatic forces on vertical plates. Okay, the calculations that we did a few minutes ago were all for horizontal objects lying under so much depth of a fluid. Now we're going to do the harder problem, and that is a vertical plate. And the hardest part is just visualizing what the problem actually is. Right. So what we have is a some kind of object. Let's say we've got a, let me turn that to a different color here. Some object, and it's sitting vertically, say on the bottom of some tank or on the bottom of the ocean floor, and it's submerged. There's some water level above it. Okay, so if we were thinking of this as a horizontal, we would have to consider the pressure of the water directly above it. But this is vertical, and we assume that in the long direction from here, we're just ignoring this. So all this part out here, this is ignored. And this is a two-dimensional problem. And all we care about is the face of this object. Okay, now look at the pressure. Remember I said that when you're at a certain depth, we'll say at a depth here, there's a pressure, and that due to the water above this, the column of water above this point, and the pressure here is being exerted in every direction. Particularly at this depth, this much of the plate will feel pressure due to this column of water that isn't really right above it, but in a sense is right next to it. So again, this is a little bit hard to visualize, so we're going to make a sketch. We'll do this better in a few minutes. Sketch the shape of the vertical plate. Here I sketched a rectangular shape. Add the depth of the water above the plate to your sketch. Then you draw in a coordinate system having to do with this vertical plate. Now, I let the y always be this vertical direction, and I put the origin or the value of y equals 0 at the bottom of the plate. This is what I do. Other people put y in the middle of the plate equals 0 in the middle of the plate. There's other things people do. This is what I do, and that's what I'm showing you here. If you put that origin in certain locations, you can make your calculation very difficult. If you put it in other locations, you can make the calculation easier. Right now I'm putting the 0 at the bottom of the vertical plate. So here's some better pictures. Let's say I want to calculate the pressure on the end plate of a circular drum. Okay, this is going to be a vertical end plate, and it's going to be circular. This is okay, this is the end of the circular drum. I forget that it's on a drum, and all I look is at the circular end plate that I've drawn here, assuming this is to be totally a two-dimensional object. That means it lacks any other dimension other than the ones that are seen right here. Now here's a sideways look at my problem. Remember, this dimension right here is really 0. So all we're looking at is the face of this plate. So the plate is on its edge. The fact it's connected to the drum, I've totally forgotten about that. Not that I haven't forgotten about it altogether, but that's a separate problem from the one I'm doing. I'm looking at the pressure on the vertical face of this plate. Here is a column of water next to it. It's right here. Okay? Now there's pressure on the water depending on how far each section of the plate is submerged. Right here it's going to feel the pressure due to all that weight above it. The point at the bottom of the plate feels pressure due to a bigger column of water because it is more submerged. The bottom of the plate is more submerged than the top of the plate. The deeper the water, the bigger the pressure. For the first example, let's do a rectangular plate, since the circular end plate actually is a little more complicated. So the goal here is to compute the force on the end of a submerged box. The end of the box is a rectangle, 2 feet by 3 feet. and the box is under 14 feet of water. Now you can interpret this different ways, but the way I look at this is that from the top of the box to the surface is 14 feet. So from the bottom of the box to the top of the water is 16 feet because the box is 2 feet high. So here's a picture of my box. That's in red. That's the end plate of the box I'm worried about, and I'm going from y equals 0 is the bottom of the box, y equals 2 is the top of the box, y equals 16 is the top of the water that's above the box. Now I'm not talking about this column of water that's directly above the box. Instead, what I'm really talking about is the column of the water next to the box. Okay. So the little point down here is going to feel pressure due to 16 feet of water pushing on it. The point right here is going to feel pressure due to 14 feet of water pushing on it, because that's all the water that's above that point. So that means I've got different pressures at different places all along the face of this box, and I have to add up all of those in order to get the total force on the box. Because using the coordinate system from the previous slide, we need to find the pressure as a function of y, because it's going to vary. Remember, at the bottom of the box, the pressure was due to 16 feet of water. At the top of the box end, the pressure is due to 14 feet of water. So I need an expression for the depth of the water, and the depth of the water is 16 minus y. Now, once I write an expression like this, I usually check it. I check it by making calculations at the end points, at the endpoints of the parameters of interest. So if I'm thinking, is this right? Well, what is the pressure at the surface of the water? When y equals 16, you're at the surface of the water, the pressure better be 0. So gamma times 16 minus 16 is 0. That's true. At the depth of 16 feet, that means at the bottom of the box, I need to feel pressure due to 16 feet of water. When I substitute that in, y equals 0, I get P equals gamma times 16, which is correct. So that was just a little side calculation to sort of verify that I've written the right expression for the depth. I believe that the depth is 16 minus y. Okay, now here's how these vertical problems are done. You divide the vertical plate into little horizontal strips. The height of each strip is delta y. The width of the strip, in this case because it's rectangular, is 3 feet. Therefore, the area of each little strip is 3 times delta y. The force, assuming the pressure is constant in each strip, the force equals the pressure in each strip times the area of the strip. Here's the pressure, gamma 16 minus yn being the y value in the middle of the strip, times 3 times delta y, and now I'm going to take the limit. Let's look back at the other slide to really see what we're doing here. Here's the plate, divided into little strips. The height of each strip is delta y, or I've written dy over here. Okay. The width of the strip is 3. The area of each strip is 3 times dy. Each strip feels a pressure, and the pressure, say, felt by each strip is going to be gamma times the height of the water, or the height to the surface of the water above it. So that's 16 minus y. Okay, so the force is the area, is pressure times area. Pressure is a specific weight times the depth of the water at this particular strip. Well, let's say this is the nth strip. Is y to the n times the area, which is going to be 3 times delta y. And that's what we're doing here. Same old calculation we always do in calculus. Divide into little strips, divide into little sections. Hopefully you can take little rectangles or some little object that you know how to calculate in each little section. That's the whole goal. Then add them all up and take the limit. And when I take the limit, I now have a definite integral. It goes from y equals 0 to y equals 2. That's because the coordinate system that I had before, that didn't work. Okay. Y equals 0 was the bottom of the box. Y equals 2 was the top of the end of the box. So here's the box sitting here between 0 and 2, and I'm integrating from 0 to 2. Here's 16, which is the top of the water. Okay, 0 to 2. Here's the first expression. Gamma times 16 minus y is the pressure, and 3 dy, or delta y, is the area. It's easy to calculate, and I get 92 times gamma being a specific weight. So that's the force on this end plate, a rectangular end plate of a box submerged under 16 feet or 14 feet of water. If the fluid happens to be gasoline with a gamma specific weight of 42.5 pounds per cubic foot, then the force is about 4,000 pounds of force felt on this entire vertical end plate of this box. This is a typical calculation for a vertical plate.